Design of experiments, or DOE, is a statistical framework. It allows you to map the exact mathematical relationship between the inputs you control and the outputs you want to measure. The workflow follows 6 chronological steps: describe, specify, design, collect, fit, and predict. Software manages the complex calculations in 5 of these phases, leaving the collect step as the point where you interact with physical reality. We can see this in action by optimizing the strength of brewed coffee. We have 4 control variables: grind size, water temperature, brewing time, and coffee charge. We also have 1 environmental constraint: the specific workstation or station where the brewing happens. Applying this strict framework allows us to translate these messy physical components into a matrix of controlled, actionable data. Our first software task is to define the goal. The default setting is maximize, but pushing coffee strength as high as possible creates a bitter product. Instead, we change the target to match target, defining a strict acceptable zone between 1.2 and 1.4 on the refractometer. Next, we input our 4 physical variables. We categorize grind as a discrete factor with 2 exact settings, while temperature, time, and charge are logged as continuous data streams capable of sliding along a numerical scale. Because our brewing happens across 3 physical workstations, we must introduce station as a blocking factor. The software uses this constraint to mathematically distribute our 12 available trial runs, ensuring no single workstation skews the final results. With those parameters set, the software builds a customized blueprint. It dictates the exact randomized combinations we need to test across our 12 physical runs. Locking in these structural constraints before brewing a single cup guarantees that the data we collect later will be mathematically sound. Once the 12 physical trials are complete and the results are recorded, we move to the fit phase to build our predictive model. This report shows the initial statistical breakdown of our experiment. The key metric here is the p-value, which measures how strongly each specific factor influenced the final coffee strength. Look at the column of p-values. In statistics, a value greater than 0.05 indicates that a factor lacks significance. Based on that rule, spot the factors failing to influence the brew. Temperature and grind fall well above the threshold. We remove them from our model to clear out the random noise they generate. Rerunning the model with only the verified active factors, time, charge, and station, yields tighter, more precise parameter estimates. Dropping statistically weak variables does not diminish the scope of the experiment. It focuses our attention strictly on the true mathematical drivers. This brings us to the final step of the workflow: predict. We can now manipulate isolated variables in a simulated environment to dial in the optimal recipe. This graph shows the prediction profiler in action. The upward trend lines indicate a clear operational logic. Increasing the brewing time and adding more coffee charge predictably drives the overall strength score higher. Our blocking factor is missing from this default view. Manually including station into the grid reveals a critical physical anomaly. Shifting the simulation from station 1 to station 3 drastically drops the predicted strength from a highly over-extracted 1.44 down to a weak 1.18. This presents a clear real-world implication. Before we attempt to standardize our global recipe, we have to investigate the physical hardware and calibrate performance across our 3 brewing stations. The exact same analytical principles apply far beyond coffee. This framework scales up to manage multiple interacting variables across complex industrial, chemical, and manufacturing operations. Rigorous mathematics will isolate the true signals in your data, but resolving the physical anomalies those signals uncover requires human critical thinking.